actually study this quantity in the context of complex frequencies. So that omega is not a real quantity, but it consists of a real part and an imaginary part. So we always say that the time dependence of a solution looks something like that. But in this case, then the time dependence has an oscillatory part plus an exponentially decaying part. And that's what I mean by complex frequency. When we encounter complex frequencies, actually we do encounter complex frequencies a lot of times in our life, in engineering. Say if I have a LC resonator, then the resonance frequency is pure real, given by this quantity over here. Okay. However, if you have a resistor put in this LC tank circuit, then your resonance frequency would consist of the real part plus the imaginary part. You can work out the resonance frequencies quite easily. And what it means is that if you excite this system and pull the source away, okay, you excite it and then put the driving source away, or you can put a voltage source here, excite it, and then turn off the voltage source and short circuit it. The first system will resonate, will oscillate with this frequency. But the second system, if you excite it with the voltage source and turn it off, it will oscillate with this frequencies plus a decaying part. Okay? So you do encounter this kind of complex resonances in real life. And you can also think of this happening in anything that dissipates energy, like if you have a cavity. If you have a closed cavity, you can have a resonance frequency that's purely real. Okay? But if you open up this cavity and make a hole in it so that energy can leak out, then the resonance frequency will have a real part plus an imaginary part, because the resonance frequency of it is not real anymore. Okay? You think of a lot of systems like that, like if you have an antenna hooked to a source, you excite the antenna with the source and then you turn the source off, making it a short circuit. Then any remnant energy in this system would have to behave like that. Okay, so such a kind of system is possible to set up. And we study the conservation of this quantity in the presence of complex resonances and see what we can gather from this picture. So it's quite easy to show that divergence of this is equal to H star dot curl of E minus E dot curl of H star. Okay, this just follows from the vector identity that we have, that divergence of A cross B is B dot curl of A minus A dot curl of B. Okay, we just invoke this vector identity to get that line over there. And then we invoke Maxwell's equations next. If we invoke Maxwell's equations, then we have curl of E is I omega, it should be B, okay, but let me see what I'm using. Yeah, it should be B. Curl of E is I omega B, okay, and then E, the curl of H is I omega B plus J complex conjugate. Okay. Curl of H is equal to this quantity over here plus that, and then if I take a complex conjugate at that quantity. So what I have eventually is that this quantity becomes I omega H bar dot B plus I omega E dot B complex conjugate a complex quantity. Okay, I have this as my quantity. But please bear in mind that omega is complex, so I need to put a complex computation over here. Okay. Yeah, this conjugation turns this into a plus I, so that makes a minus over there. Okay. So let's put this in the presence of material media, so that D is epsilon E plus P, and this is due to material media, and then B is mu naught H plus M, and due to the quirky nature of things, we always write the second equation in this manner. P is associated with no epsilon naught, but M is always associated with mu naught. It is just a matter of convention. And if we call this S, this quantity S, then we have divergence of S. And now if I substitute this in there, I will get I omega mu naught H squared, because I will have H conjugate times H, I get H squared, okay? And then if I substitute this in there, I would have this being conjugated, okay? E conjugated would be this conjugated, this conjugated, this conjugated. Okay, the second term will give me minus I omega epsilon naught with a complex conjugation here with the E magnitude square. Okay. And then I will have the leftover terms, which comes from this term, plus I omega mu naught H dot M, okay, which comes from this cross term over here, plus this other cross term, minus I omega star E dot P star minus E dot J star. Okay? So, in the case of a pure harmonic signal, okay, if omega double prime is equal to 0, we have pure harmonic signal. You have pure harmonic signal, then we'll see what happens there. And then we also study the case of omega double prime not being equal to 0 and see what kind of inference we can make about this thing. Okay, we make the assumption that P is equal to epsilon naught chi P dot E. Okay, and this is the material medium description, and then M is equal to pi sub M dot H. Okay, that essentially we have a linear medium. And if that is the case, then this equation if I were to take its real part, okay, if I were to take the real part of this equation, then I will have divergence of the real part of S being equal to the real part of this quantity. Because omega can be complex, the real part of that quantity is equal to omega double prime mu naught H squared. Okay, and then the real part of this quantity will be plus omega double prime. So if I take the real part of this quantity, because of the conjugation, I get a plus sign instead of a minus sign, so I get a plus quantity. So the real part of the first two terms give me that. and then followed by the real part of the last three terms. If I substitute that in there, I get the real part of the last three terms to be equal to I omega mu H conjugate M is equal to chi M H equal to chi M dot H. And then the real part of this quantity, which is I omega epsilon naught E dot chi E conjugate dot E star. Okay, plus the last term, which is E dot J. Okay? So if I take the real part of this quantity, I get that. I take the first case first, where omega prime tends to 0, omega double prime is equal to 0. If I take this first case first, I would consider the pure time harmonic case. I consider the pure time harmonic case, then this first term disappears. Okay, this first term disappears, and that if I were to assume that there's no source driving the system, then there should be no energy entering the system, and divergence of real of S should be equal to 0, okay, because there's no energy entering or leaving the system. And that term also on the right hand side should also be 0. This should also be 0. Okay, because I'm assuming that I don't have any source driving the system. And in order for this to be 0, omega is pure real now. Okay, there's no imaginary part because I'm considering this case over here. Then the only thing that I could have to make this equal to 0 is for this term to be pure imaginary and this term to be pure imaginary. Okay? In order for this term to be pure imaginary, these are actually cancelled. How can I make this term pure imaginary? I will have to make this term pure real. And how can I make this term pure real? What condition do I have to put on chi sub n to make it pure real?
Symmetric.
Symmetric is not sufficient. Symmetric is one possibility, but not always true. Hermitian, right? If chi sub m is Hermitian, if chi sub m is equal to chi sub n Hermitian, which is the short form conjugate transpose. Okay, Hermitian is this dagger means conjugate transpose. If this is true, then this will always be real. I can prove that very easily, right? And if I take the conjugate transpose of this whole quantity, transpose and then conjugate, I use the matrix algebra. When we write something like this, there's actually a transpose associated with this vector over here, but physicists usually don't write that. Okay, image vector transpose times matrix times vector. Okay, if I take the conjugate transpose of this, I will get this quantity transpose times of m transpose dot H star. This is, I first do the transpose operation, I get that. And then I will do the conjugation operation, I get that. This is conjugate transpose, and I put a dagger to represent that. Okay? So, if this is a real quantity, if this is purely real, its conjugate transpose should be itself. Okay? It will be itself only if chi m conjugate transpose is equal to chi m. Chi m conjugate transpose is equal to chi m, then its conjugate transpose will be itself. And if you have a number, if you take its conjugate transpose is equal to A, that means that that number must be a real number. Okay. So in order for this to be a real number, this chi m has to be Hermitian. If this is a real number, then this is an imaginary number. And similarly, if this chi sub E is Hermitian, this second quantity here will also be purely real. And then this will be purely imaginary. And when we take this real part, it must be 0. Okay? So, if chi m conjugate transpose is equal to chi m, chi e conjugate transpose is equal to chi e, it means that the medium absorbs no energy because the right-hand side, if there's no source driving the system, if you take any part of the medium and apply this relationship, you find that there's no net energy entering or leaving that point. Okay, so this must be lossless medium. So if a medium has this kind of relationship, that medium must be lossless. The tensors are Hermitian in their property. Okay. Are there any questions regarding this one? I think more interesting is the case when omega double prime is not equal to 0, which means that omega is equal to omega prime plus I omega double prime. But let's assume that omega double prime is still much less than omega prime. So it's almost time harmonic, but not exactly time harmonic. So there's a little bit of radiation loss or radiation damping, or maybe due to some resistive loss somewhere, that this is true. And let's study the case of when this is true. And if you look at the relationship again, then what we should have is that so we study this case, then the first term will not be 0. The first term will not be 0. And then what happens to the second term? We make an approximation that chi sub m at that complex frequency is going to be equal to, by Taylor series expansion, chi sub m at that frequency plus a Taylor series expansion part. Okay, this is an approximation. Perform a Taylor series expansion about this point, omega prime. So I can approximate chi sub m with this approximation, and then I can do the same thing for chi sub e. It's going to be approximately equal to chi sub e omega prime plus I omega double prime. Now I can substitute this back in here, assuming that omega is complex. And if I were to do that properly and rewrite the relationship again, I will have divergence of the real part S is equal to omega double prime times the first term, which is still there, and then taking out terms from the first, second, and the third term, okay, we can assume that there's no source for this special consideration. So if we extract the quantity and assume that chi sub m is given by this quantity plus a small part over there, then this part is going to be like, let me see, I omega prime this first quantity over here, okay, is going to be I omega prime times this term over there. Let's assume that that term is coming from a lossless medium. So the first term will be purely imaginary, the contribution of this term, when we plug this term in there. And if this is omega prime, this term will be purely imaginary. So we will not account for it. But then this omega double prime term, it will multiply by, let me see what it will multiply by, the omega double prime term. That is a small term. Okay. Okay, so there will be a small term coming from here, which is equal to minus omega double prime mu naught h star chi sub m dot h. Okay, this would have the first term that's related to omega prime, but that term is pure imaginary. Okay, the second term, which is omega double prime times this thing, will give rise to this term, which is real. Okay, that will contribute that term over there. And then there will be this other term. This other term, omega double prime, multiplied by omega prime, will give you something that is pure real. Okay, so there will be an additional term that looks something like this. Omega double prime, mu naught h star dot e chi m d omega prime dot h. Okay, so can you see how the third term come about? The third term comes about because of this term. When substituted in there, multiplied by the omega prime term, give you omega double prime, omega prime term. Okay, can everybody see that? How this term comes about? So you do the same thing. Let's assume that J is equal to 0, assuming that we're not pumping any energy into the system. Okay, so we repeat the same thing for this term. We will have something that looks like this. Something that is similar to that term over there. Okay, and then a term that looks similar to this because of the complication we had over there. Okay, omega double prime, epsilon e dot e chi e conjugate the omega prime, and then dot with e. Okay, so that is how the energy conservation equation looks like. This is assuming that a system is undergoing complex resonances. Okay. But we assume that omega double prime is very, very small, so that this quantity still has the meaning of time average power flow. This is real part of E cross H conjugate. Remember, we proved that this is equal to E cross H equal to this quantity by assuming that this is a time harmonic signal. Okay. We assume that omega double prime is very small, so that this is quasi-time harmonic, so that this concept is still true, and that this is still somewhat the time average of this quantity, because this is quasi-time harmonic. And now if you look at this quantity now, it is related to the right-hand side in this manner. And you can think of this right-hand side has been omega double prime. Let's see what I have here. Omega double prime times W. Okay, if you look at every term here is multiplied by omega double prime. I can lump everything that is multiplied by omega double prime and call it W. And W has the physical meaning of stored energy because it says that divergence of a power flow, power density, okay, is equal to omega double prime W. And W must be proportional to time in this manner. Because of the way we assume that everything that we have is going to have this kind of time dependence, and omega is slightly complex, so that this will be equal to I omega prime t e to the minus I omega double prime t. Okay. Hence, every term that we have will be proportional to the square of the quantities. Because they're proportional to the square of the quantities, it has to decay with time in this manner. Okay, there's always a complex conjugation part that get this term to cancel each other. The only time dependence left is this time dependence. So you can think of that W has to be something of this form, and this must be minus partial T of W. Okay, so this is reminiscent of your charge conservation equation. All conservation equation looks something like that. Okay, now we have an equation that says that the real Poynting power flow or power flow density is equal to partial T of W. Okay, and this relationship is proven for the case when omega double prime tends to 0. Okay. So this quantity that we have in here must be some kind of a energy density. Okay. There must be some kind of energy density. The rate of change of energy density is power flow, is what it says. So now we can identify what W is. W will consist of there's something wrong with this argument, isn't it so? Is this time dependence correct? What? Should be twice, right? Because if the E and H pairs are going like this, then all the quantities that we have are proportional to the square of the quantity, so this is twice. Okay. So this quantity here, omega double prime times W, should be so if I put this quantity over here, okay, and then equate this to be omega double prime over 2, I think things will work out correctly. And if I define this to be that, okay, because this has this time dependence that will bring a factor of 2 out on that be correct. Omega double prime W over 2 is equal to, no, that should be And then if I put a factor of 2 here, okay, if I put a factor of 2 there, and if this W is something like that, then this is just dDW. So this quantity here is just partial T of W. And I actually don't need a minus sign. I don't need a minus sign. So that should do it. Okay. So I should define this without the minus sign. Is this?
Actually, if you define omega equal to omega prime plus I omega double prime, the time dependence of omega double prime should be e to the omega double prime t, not negative sign.
Not negative sign.
Right.
Because of this?
Yeah.
Oh, you're right about that. Okay, because of that quantity, because of the way I assume things this way, you're right about that, okay? So this time dependence should be, so I messed this up, then this should be plus omega double prime, because this will be I omega prime t. Thank you for pointing that out. This should be correct. Minus, minus. And then, if that is the case, then W should be proportional to this quantity. So if I differentiate that, I get 2 omega double prime. And if I differentiate this, I should put the 2 minus 2 here. Minus 2, and this should be minus 2 then. Minus 2 quantity. Then everything turns out right now, right? No more mistakes, am I right?
Is the omega double prime must be negative in this definition?
Right, in this case it should be negative, otherwise it wouldn't decay with time. Okay, of course it can be positive too for an active medium. If you have a lasing medium, it can be positive as well.
Another question is, so we're still assuming even for the lossy medium that the chi's are Hermitian. Just
Chi are Hermitian,
just plug in
right.
a complex.
Right, right, to the leading order. The leading order chi are Hermitian, so that these quantities are real. So when you take the real part, you only take up this imaginary part. So now I can equate my W. I can say that my W is actually what we found in textbook for the first term, which is pleasing. Okay. The stored energy in the free space part is equal to that, the first term. And then the second term is rather complicated. Okay, it's rather complicated. It's this term plus this term over here. This chi m term plus this term over here. Okay? But you realize that chi m plus omega prime d chi m d omega prime, and then there is something, should be something, right? So this is just equal to d omega prime of omega prime times m, right? If I do that, so it can be compressed. These two terms can be compressed into one term. I think I'm doing it correctly. Okay, so I can write these two terms as one term and compress it as one term, and then these two terms can also be compressed as one term using that trick over there. Then I can write the stored energy for the second part as being half epsilon naught E dot omega prime. Let me, in my lecture notes, I have this chi E from first, E omega prime dot E conjugate plus half mu naught H conjugate dot E omega prime chi M. This should be parenthesis over here, E omega prime dot H. Okay? So the important thing to learn here is that in addition to what you learn in your undergraduate course for the stored energy in the material medium, that's vacuum part. But for the material medium part, the stored energy should be given by this term in the electric field and this term in the magnetic field. Okay. And if the medium is non-dispersive, then this term will disappear. You only have that term. But as we said before, it's not possible for a material medium to be non-dispersive because they are all due to moving molecules, and moving molecules have inertia. You cannot change things instantaneously in material medium. So this term is always there. And this should be the stored energy in the material medium. This should be the stored energy in the material medium. So unfortunately, some textbook will just change this to mu naught to mu.